SAP 2000 offers a powerful nonlinear static pushover analysis option which tracks hinge formation and helps to identify the failure modes of the structure. Pushover analysis may be performed on either existing or new construction. For the simple 3D steel frame model shown, we have assigned auto-select section lists to the columns and beams. We will run a linear elastic analysis and then a design where members will be selected based on SAP 2000's optimized design capability. The model will be initially subjected to dead, live, and response spectrum loads. We can now run the analysis. Once the analysis is complete, we start the design to optimize the members. The selected sections are displayed on the model. It is these sections that will be used for the nonlinear pushover analysis. The next step is to assign hinges to our line objects. We unlock the model, select the beams, and then go to the Assign Frame Hinges command. First, we will use the auto hinge property located at 0 relative distance. Auto hinges can be generated from either FEMA or Caltrans specifications. Here we will use FEMA hinges. We have a choice of several different types of hinges, and we will use the steel beam flexure hinge in the M3 degree of freedom. Next, we will add another hinge at the other end of the beam. We will use the same hinge property. Next, select each column and go back to the Assign Hinge command. We will follow the same procedure as done with the beams, except that we will use the FEMA definition for column hinges. We can verify the hinge properties generated by going to the Define Hinge Properties command. The user should always verify that the calculated behavior is appropriate for their model. Next, select All and go to the Assign Frame Hinge Overwrites command. Check the Auto Subdivide Line Objects at Hinges checkbox. This will discretize the member and can give better results. Next, we will define the pushover load case. However, before we do that, we need to set the dead load case to nonlinear so that the program can use this case as the starting point for the pushover. We will call the new pushover case push, which will continue from the dead load case. The load will be applied as an acceleration in the UX direction with a scale factor of -1. We will use displacement control and will push to a displacement of 12 inches at joint 1. We will also save the analysis at multiple states. Joint 1 is located here. This is our displacement control point. We can now run the analysis. We will shut off the response spectrum case, as this was needed only when doing the linear analysis for member sizing. Once the analysis is complete, we can display the deformed shape for the pushover load case. We can move through the various steps and see what hinges are forming and where they are on the force deformation curve, such as immediate occupancy, life safety, or collapse prevention, as indicated by the color of the hinge. Next, we will plot the pushover curve. First, for base shear versus displacement. Notice how the base shear drops off as the hinges form and reach different states. We can also plot the capacity spectrum, with the capacity curve in green and the demand curve shown in yellow. The demand curve is plotted here for seismic coefficients of 0.4. However, we can easily vary these coefficients to see how the demand curve slides out on the capacity curve without having to do another analysis. The point where the two curves intersect is called the performance point, and it is this point that represents the global behavior of the structure. Even when the structure looks to have adequate capacity from a global standpoint, it is always advisable to check that local collapses are not occurring, which we will do now. Note that for this demand curve, the performance point has a period of 0.585 seconds. When we look at the demand capacity table, a period of 0.585 seconds occurs between the 5th and 6th steps. When we display the deformed shape for the 5th step, we see that the largest hinge is at the life safety level, and that at the 6th step, the hinge is at the collapse prevention level, which means that there will probably be no collapse locally for this level of earthquake. We can also plot hinge results. Selecting the 10H2 hinge, which was a beam hinge, we can plot the hinge path against the backbone. We start at step 0 and then step through the different states, which are displayed here. At the end, the program has automatically softened the drop in order to achieve convergence. And although it does not follow the hinge definition exactly in the latter stages, an accurate representation of overall ductility performance is still achieved. Lastly, we can plot forces in the model. Here we will plot the moment, and we can step through these as well. This concludes this tutorial.